Hi, welcome to the inverse of a square matrix. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. I love my jobs, by the way. Greatest job on earth. I can't believe they pay me, but shh, don't tell my bosses. Alright, this is for Math 1508, Pre-Calculus at UTEP. Chapter 8, Matrices and Determinants, comes to us from Larson's 10th edition pre-calculus text in section 8.3, the inverse of a square matrix. This is actually a first part of a two-part video, finding the inverse of a square matrix. We're going to keep it to a 2x2 for now. And then in part 2, I'm going to tell you why we need the inverse matrix. And the hint is, that's how we do division of matrices. We don't divide, we multiply by the inverse. But that's in part 2. Check it out if you want to know more about that. So first of all, let's define the inverse of a square matrix. Let A be an n by n matrix, and let I sub n be the n by n identity matrix. If there exists a matrix a to the negative 1, such that a times a to the negative 1 is the identity matrix, and the multiplication in the opposite order is also the identity matrix, then a to the negative 1 is called the inverse of a. Notice we were using the inverse notation before we even defined it, but that's alright, we'll go with it. A to the negative 1, a inverse. Not the reciprocal, just like functions, it's not a reciprocal. This is an object that we're working on, so not a variable. It's inverse, not reciprocal. Alright, so by definition, if I multiply a matrix by its inverse, I should get the identity. So if I want to show that B is the inverse of A, I'm going to multiply in both orders to show that I have the identity. So I'm going to take the row to find AB. I'm going to take the rows of A and multiply by the columns of B. So row 1 times column 1 goes in row 1, column 1. Row 1 times column 2 goes in row 1, column 2. Row 2 times column 1 goes in row 2, column 1, and row 2, column 2 goes in row 2, column 2. And when we do the arithmetic, we find that, hey, cool, we have the identity matrix. But we know that multiplication is not commutative for matrices. So just because this one equals the identity matrix is not a guarantee that the other order of multiplication does. Even though our instructions show that B is the inverse of A, so we kind of assume that it's going to happen alright, but notice this time I'm multiplying B times A, so I have rows of B, 2, 1, times columns of A, 1, negative 1. Row 1, 2, 1, times column 2, negative 1, 2. Row 2 times column 1. This should definitely be a plus sign. I forgot to hit shift there, so let's just fill that in a little bit. My bad. Plus sign, typos happen. Row 2, column 2, 1 times negative 1 plus 1 times 2. And when we do the arithmetic again, we find that we get the identity matrix, and they are in fact inverses. Okay, so let's talk about how to find an inverse matrix. A lot of times in math, we're not given the, hey, here's an answer, make sure it's right. That would be nice though, wouldn't it? So we need to find, how do we find this inverse? So first, let A be a square matrix of order n. It must be a square matrix in order to have an inverse. Very important. So we were going to write the n by 2n matrix that consists of the given matrix A on the left and the identity matrix augmented on the right. So it'll look like a matrix A and then the line for augmentation, the identity matrix, and then close the brackets. If possible, row reduce A to an identity matrix using elementary row operations on the entire matrix. What your result's going to be is the identity matrix on the left and the inverse on the right. If you end up with a row of zeros, or if it's impossible to row reduce, then A does not have an inverse. And as always, you should check your work by multiplying in both orders to see that the definition holds. That is, A times A inverse equals the identity matrix. Now this, that I call the hard way, is the method that works for every single square matrix that you have. No matter the size, you can find the inverse using these steps. The steps are not hard. It's just sometimes that you don't want to do all of those steps if there's an easier way. But let's check this, at least one example, using this method. So we're going to find the inverse of the matrix if it exists. And our matrix is 1, 2, 3, 7. So our first step, we take A and we augment with the identity matrix, 2 by 2 matrix on the right. We already have 1 in the upper left, our leading 1, so we're going to make a 0 below it by multiplying -3 times row 1, adding it to row 2, all the way across, multiply by -3, add row 2, and I end up with a new row 2, which is 0, 1, -3, 1. Hit pause if you need to check my arithmetic. Always a good idea. Now with our given matrix, we have a 1, we have a 0 below it. We have a leading 1 in row 2, so we need to make a 0 above it. So I'm going to multiply -2 times row 2 and add it to row 1, and I'll cancel out and make a 0 here. So -2 times row 2 added to row 1 is my new row 1. -2 times row 2 added to row 1 gives me 1, 0, 7, -2. Notice I now have the identity on the left, which tells me that my inverse is the matrix 7, -2, -3, 1. See, it's not hard. I said the hard way. And you're thinking to yourself, man, if that's hard, what's the easy way? Don't worry, we'll get there in a minute. Hard is a comparison, not that this method is difficult. So I should check. I should multiply A inverse times A and A times A inverse to make sure they're inverses, but sometimes you got to have confidence in your work too. Okay, so we're going to find the inverse of the matrix if it exists. Here's an A, which is 4, -1. Second row, -3, 1. Augmented, I didn't put the line in the middle. Laziness, really, is what it comes down to. I need to make a leading 1, so I divide the entire first row by 4, or multiply by 1/4, whichever you prefer. Now I need to make a 0 below it, so I want to multiply by 3 and add to row 2. 3 times row 1 plus row 2 is the new row 2. And I have 0, 1/4, 3/4, and 1 for my new row 2. Notice even though I used row 1, I went back to the original for my matrix. The same result we had at the bottom of the last slide. Now we want to make a 1 in row 2, a leading 1, so we'll multiply by 4, multiply everything by 4. 0 times 4, 1/4 times 4, 3/4 times 4, and 1 times 4. Fantastic. I have a 1, I have a 0, I have a 1, I need to make a 0. And I know it seems counterintuitive. Right here, I could have added these two and everything would have been gravy. But we always make the 1 first so that we don't get off track when we have these exceptions. So I made the 1, and then to make a 0, I multiply by 1/4 again. So it takes it back to this that we had. Add row 1, and I end up with 1, 0, 1, 1. And I have the identity matrix on the left. And this is my inverse. A inverse is 1, 1. Second row, 3, 4. And again, I should multiply. I'll leave that to you to see if that's actually the inverse. And that's not hard. I mean, really, it's not hard. But, you know, we're always looking for shortcuts. Sometimes too often. And the fact is, to find the inverse of a 2 by 2 matrix, we could use a special formula. Just like some people don't like factoring quadratics, we could use the quadratic formula to find the solution of any quadratic equation. There's also a cubic formula. If you don't feel like finding the zeros of a cubic function, you could use the cubic formula, but nobody knows the cubic formula because it's long and hard. And similarly, there's a formula for finding the inverse of a 3 by 3 matrix, but you don't want to see that. Sometimes the, quote, shortcut formulas are actually more difficult. It's not true for a 2 by 2, so let's take a look at it. If you have any 2 by 2 matrix, capital A, given by entries A, B, and row 2 is C, D, then the matrix is invertible, so an inverse exists, if and only if A times D minus B times C equals 0. We call this the discriminant. No, we don't. We call that the determinant. I had quadratics in my head. This is the determinant. It determines if there's an inverse or not. Moreover, if this is non-zero, then I know exactly what the inverse is going to be. The A inverse will be 1 over that value, AD minus BC. And then we're going to switch the places of A and D, change the sign of B, change the sign of C. And then we'll multiply through by this scalar in order to finish it up. Let's do some examples. We're going to find the inverse using the formula. So I have the matrix 1, -2, second row, negative 3, 2. I'm going to check AD, so 1 times 2, minus B times C, so negative 2 times negative 3, so that's 2 minus 6. 2 minus 6 is negative 4. Since negative 4 is not 0, we know the inverse is 1 over negative 4, right, my determinant. Switch the places of A and D. Change the sign of negative 2, change the sign of negative 3. And I'm going to finish it off by multiplying through by negative 1/4. So that'll be a 1 over negative 4 times 2. That's a negative 2/4 or negative 1/2. Same over here. Negative 3/4 and the negative 1/4. Wow, my brain just got stuck there for a minute. It happens. We'll go with it. Again, AD minus BC, so we'll take negative 12 times negative 2 minus 3 times 5. 24 minus 15 is 9. We know that's not 0, so the inverse will be 1 over 9 times. Switch the places of the negative 12 and negative 2. Change the sign of the 3, change the sign of the 5, and then multiply through by the 1/9. There's our inverse. And you could check by multiplying and make sure we're right. Now, you know, I haven't had you try one for a while, so I encourage you to pause it because the next slide is going to be the answer. Don't cheat. You're only cheating yourself. I'm trying to stall here a little bit to convince you to pause, give yourself a, work it out, see what happens. Find AD minus BC. I know, big numbers. Trust me, this is going to be a good one. And then you'll switch the places, change the signs, multiply through by the reciprocal of the determinant. Let's see what the answer is. So AD minus BC gives us 1. This is 133 minus 132. I know, they looked horrible, but they're not. Since this is not 0, we know the inverse is 1 over 1. Right, there's my 1. Switch the places, change the signs. When I multiply through by 1, well, that's the easiest thing I could possibly do, and I get that nice little matrix. Inverses using a nice formula, but what we're going to talk about in part 2 of this video is how we can use these as a, quote, division for matrix operations. Wow, my brain got stuck again. It must be time to end the videos for the day. Part 2 coming soon, but I can't guarantee when. Thank you for listening.